So, welcome. I'm glad you guys had a break because I was worried that I was going to have to make you do jumping jacks in order to stay awake during my talk because I have formulas. Have you guys seen my radio astronomy formulas YouTube videos? I've been putting together all the formulas that I didn't know that I've looked at before, but I probably couldn't reproduce from memory for you. So I said, well, why don't I just put these out in videos and give some example problems and make them short so you guys can look at it like what's the gain of a parabolic dish and make a couple examples so you guys can quickly look at those things and say, okay, here's how I can figure out what my gain is on my dish and, you know, what's the loss and pointing loss and things like that. So the Deep Space Exploration Society, which is I originally started at before SARA, is putting two 12-foot dishes for an interferometer together. And of course, Wolfgang's presented at his interferometer, and a couple other people put interferometers together, amateur interferometers, and it looked really cool that we can actually get very good precision on using interferometers if we didn't have a big dish. So my thought process is that, hey, why don't I see if I can use all these formulas to model an interferometer, a two-element interferometer. Then you start looking at the radio Jove. Who's got a radio Jove, two-dipole radio Jove system? You have an interferometer, right? It's not an east-west interferometer like Wolfgang has. It's a north-south interferometer. Well, that means that you've got actually your beam width and you're actually able to point the beam at a certain elevation angle. All right. And so the beam width goes down here. So what if I combine the two? So I first started, by the way, in Excel. All right. And I actually got this working in Excel. Very, very fun if you want to do it in Excel. But then I got my MATLAB, my free MATLAB program. I was able to do a MATLAB thing, and it gives a lot better pictures. So I'm going to show you the MATLAB version of this. But using the formulas from all that radio astronomy formulas that I did. Okay, so that's why I wanted to make sure you guys were wide awake. Didn't eat too many sugared cookies before this talk. All right, so let's look at the gain of a parabolic dish. So you look at that thing, and there's the antenna efficiency, the diameter, and the wavelength. Okay, if you know those, so what's the wavelength of what you're looking at? And here I'm going to use 1420 mostly for hydrogen. Diameter of the dish all the way down from 0.5 to 3 meters or even larger. Efficiency, I usually just 0.65. You can vary that too if you wanted to. So that's the gain of a standard dish. Now, what happens when you do a drift scan? A drift scan is your source here, and let's call it a constant source, doesn't matter what it is drifting across your fixed dish. Say you're pointed at south, and you got this thing drifting across. Well, the gain of a dish is, on the edges. In the center, it's the highest gain, right? But on each edge, it drops considerably based on this formula. And when I call pointing offset, is I'm saying 0 degrees is straight on. Anything off number of degrees is the pointing offset, either plus or minus. Half power beam width is another thing. It says, for this size dish, what's the half power beam width? So the beam width here, the beam width is really important. That's how wide in the sky you're looking. And what we're trying to do with interferometers is drop that beam width. So we have more resolution. So just like you saw Dr. Jackson's talk, the 300-foot or this telescope out here is known for its small beam width. So it can do the resolution, make those small clumps out of the big pictures everybody else has been doing. So now can we as amateurs do small beam widths with smaller dishes? Say you had two DirecTV dishes and you put them far enough apart, you can get your beam width down to smaller levels. Assuming you have enough gain to see the thing at all, you can definitely reduce your beam width. And you don't need your big dish, a big, maybe a two, and I don't know if it really is true, 2 half-meter dishes might equal a 3-meter dish in resolution, kind of stuff. But anyway, so I put these formulas together, and you see the half power beam width formula is wavelength over diameter times 70 degrees. So obviously, if you plug all these things into MATLAB and you start looking at the pointing loss, and the left one is offset angle. So 0 degrees is the highest beam width, or the highest gain. And then, you know, as you go left or right, depending on the size of the dish, you'll get this thing to look. Now, on the right, the degrees, when you're doing a drift scan, you know, the Earth rotates 360 degrees in 24 hours. What does that mean? That means that 1 degree every 4 minutes. So all I'm doing is taking that offset angle and changing it into minutes. So you can tell how far in the future before this thing actually hits the edge of that dish, and then transverse the entire dish and goes to the other side. So that's the showing in the minutes, plus or minus 0 point when it hits the center. So at this point, you can tell using drift scan where I'm going to get the highest, where my gain's going to be as you get your object drifts past your antenna. Okay, so that's all I did there. So that curve there, based on your dish size and your elevation, or not your elevation, but your beam width and stuff, you really, that's what you're going to get. That's the maximum gain you're going to get out of that antenna doing a drift scan for an object going through you. All right, so anything past that, there's something going on. So we start with that with a single dish. Okay, and so there's an east-west and a north-south component. So the assumption here, and by the way, this is a thought experiment. I haven't done this yet physically. So if, you know, so some of this stuff people have actually done, but I haven't seen a combined version, a north-south, east-west one. So what I'm looking at is east-west is the drift scan normal mode. You know, you're pointing, we're south. I'm pointing south, and I've got a single dish. And so if I see an object and it's dead center and, you know, both an up and down and side to side, then I should see beam width left, right at this beam width in degrees for the thing for all the formulas. So that's what I should see in the beam width size. Okay, so what happens when on an east-west is that the beam width contracts this way, but it stays the up down, it still stays the same. So I get these very narrow windows with big long beam widths north south. Okay, so going back to the basics, what's interferometry do? If I've got two antennas that are seeing the same wavefront coming in, and they're exactly the same angle, then they will come in at the exact same time, and they will actually amplify each other. They'll add together like that. Okay. If they are 180 degrees off, they'll totally cancel each other out. So an interferometer, when you start seeing that classic fringes, you're seeing as it's going by that it's going from in phase to 180 degrees out of phase, and it's cycling. So you're seeing this fringe happen. Okay. So that's the basics of interferometry, is that wavefront coming in is a signal that based on the drift scan happening, it's seeing at different angles and therefore different time delays as it's hitting both dishes, which causes these cycles to happen. And that's why you see this up and down as it goes by. If you just had a steady source, like say I put a drone out there and I just had it steady, you wouldn't see a fringe pattern. You just see it's stuck in whatever the angle that you were looking at. So just realize that the drift is important, that the movement across the sky is important to see the classical fringes. Otherwise, you just see the points in the sky that without that. Okay, so, and you guys might have seen this from the Radio Jove kind of thing, but so I got my source, and the sources are so far apart that there is no angular difference. It's not like a source sitting here and it's hitting two different beams. It's all coming in a wave, a straight pattern. So everything is coming in this way. All right, just because I have it sitting there, it really means it's light years away. It's coming in flat. So then if you see the little U signal there, it's simple geometry that you can figure out what the U is if you know the angle, which would be the offset angle of where you're pointed to the source. So I can figure out the delay. I can figure out what the wave phase difference is between when it's receiving on antenna 2 and antenna 1. Okay, so the math is relatively simple to figure that out. It's the same stuff. You look at the Radio Joe book, they show you how they do that, but they do it a different way. All right, now I'm not trying to get you to do this, but I found this equation. My problem was, how do I convert all this to make, relate the speed of the object going across the sky, which is the rotation rate of the Earth, and make this turn into gain, right? Gain of the antenna. So I found this original one was based on having the source power, and I just basically made a modification. I said, well, if I put the gain function in the front of that, then I can actually plot what the gain of the two antennas are from the start. So here I converted it to total gain of both antennas based on drift scan. And the time of the drift scan, that WET, is basically your offset angle. Okay? And so you got the gain, we got the weight, it's based on gain, wavelength, and all that kind of stuff. So you've got all the standard formulas. The new formula, the new variable in here is baseline. So what is baseline? Whoops, I'm going to go the wrong way. The B there is the baseline is the distance between the two antennas. In general, in interferometry, the farther away you get the two antennas, the closer the fringe spacing. So you get so you want to reduce your beam width, you get the antennas farther apart. That's why you see VLA 27 kilometers across. ALMA, they put it on these big planes. They're trying to get that beam width across. That'll give you a very narrow resolution. When you see the Event Horizon Telescope, they're looking at M87 and they're looking at Sagittarius A star. And how can they see that little object? Well, they had to use a baseline the size of the Earth from end to end. That's why you see that they're using all these different things. And they had to do north-south to get the north-south versions of that. Okay, so the B is important, right? And that also affects your, how the phasing works when this thing passes by. So anyway, the new formula that I basically evolved from this top one that I got out of a book, and I'll show you the things there. Very good. And this turns into a very nice, easy formula to put into MATLAB. And okay, the other key thing, and I would write this one down because it's an easy one to memorize, is that fringe spacing, the distance, when you see that fringe happen, the distance between the two peaks, either the top or the bottom peaks, between any two fringes, is this in degrees. So wavelength over the baseline, and then you can, normally that's all you need, but then that's in radians. So you want to convert that to angle. So you times that 180 degrees over pi, and that'll get you your fringe spacing. So that gives you you see all this thing happen. What's the distance between those two peaks? That's a real easy formula, but that's the key is I want to reduce that down. When I get my two antennas, I want to reduce that fringe spacing down, which effectively reduces my beam width on my antenna. Okay, so here's an example I ran with combining those two formulas. And you see the top blue one is the one I did with the standard one dish beam width, right? But now I've added that to this a second dish. So that top one is the combination without interferometry of if I just had two dishes without interferometry, and then you got the pointing loss. So I just totally added them flatly. But now you look at the total gain fringe spacing when you just now plug that formula in as you're going an offset angle there. And you see how the fringes happen. And you see the center fringe. And the maximum gain you can have is obviously from your pointing loss. So you see the fringes fit right nicely into that formula there. So this is something based on those little equations, you guys can actually come up with your own idea of how your antenna is going to work, your two element antenna is going to work in fringe spacing, and basically what's your effective beam width. So let's look at, remember the big bubble we had before? So this is what it looks like on a two element interferometry and drift scan mode, both looking 180 degrees, or even actually you can both look north. You get this very narrow beam width, but you still got this big wide one. So if you plug all this stuff into the Ezra program, you got these streaks of very good streaks this way, but you got very poor resolution north-south. Well, how do you fix that? Well, you put a north antenna up there. But let's look at a couple things that happen. Let's say this is still a two element interferometer. So just in general interferometers, what if I change the diameter to 0.5 meters? What happens? The entire thing drops, and the end to end, you'll be picking up the signal farther because the beam width is a lot larger. So it's a small antenna, you're looking wider, but the gain is totally down. Okay, but notice the fringe spacing doesn't change. The diameter of the antenna has nothing to do with the fringe spacing. So none of the interferometry stuff, it all looks the same, independent of the diameter of the dish. Excuse me, independent of the independent of the diameter of the dish. So the next one is I put that's 5 meter, and then a 1 meter and a 3 meter dish. So you can see is that as you get bigger dishes, you start seeing that the cutoffs are a lot narrower. But the fringe spacing is the same because I'm not affecting the fringes. And I put in the model, I just put these are at 5 meters apart in baseline. Okay. So now let's change if I change the baseline distance. So remember in the fringe spacing, if I increase the baseline, my fringe spacing should be reduced. So if I change the baseline to 2 meters here, you see that the fringes are wider. So my effective beam width is bigger. But if as I increase the baseline, as you see over here, the fringe spacing gets a lot narrower. All right. And that FS is what I'm calling fringe spacing. I just calculated that fringe spacing formula right there. So you can see how that comes down as the baseline distance goes up between the two antennas. See how it works? Okay, so what does frequency change? So say I want to go from a hydrogen line to what I do here. 800 megahertz is the first one, or 0.8 gigahertz. So what does that do? It basically, that's also in the equation under the wavelength side on the fringe spacing. So you'd expect lower frequencies have smaller fringe space or bigger fringe spacing. So you see 800 megahertz, the hydrogen line's the middle one. And not only does it change the fringe spacing, but it's also in the formula for the half power beam width and the pointing loss. So the combination of frequency changes everything simultaneously. right? So you see how it's coming down here and the fringe spacing is going lower, et cetera. So the higher you go up in frequency, the more narrow you get in both fringe spacing for interferometry and beam width in general. So that's just an example of using basic formulas in MATLAB and plugging them in and seeing what you get. There's a point here for an amateur that the farther you go to the right is actually getting harder because it's so fast. It's almost easier to put say if I use the hydrogen one, to not put a big beam, not make them 100 meters apart, because your fringe spacing would be so small, you probably can't take advantage of it. So even having two dishes, just to try it out, having two dishes, 5 meters apart might be better because you can pick up stuff like this, but I don't think you can do anything with that farther one. That's almost too fast to take advantage of it for amateurs. As you get better, you can actually, plan on that. But I'd almost say, having a 1 degree fringe spacing is probably good enough for an amateur. And then if you want to get better, then you get better. But I think you would, if you get too energetic here, it's almost too hard. Okay, so I said, okay, that's that. Now, what's our example of a north-south phased array that we commonly use? With the radio Jupiter is a north-south phased array. The difference there is it doesn't matter where the drift scan is in a north-south phased array. When it hits center, it will have a phased angle based on all the parameters. So let's look at that real quick. And so here's, I'm just saying that antenna 1 and 2, and what I did is I put antenna 3 dead center in between them. The assumption here is that, yes, I'm going to see everything go by, but I really only care about when they're dead center. All three of them are even. All right. Complications, because this is a very basic model, the complications are that as it's coming by, that it's going to cause all sorts of weird interference patterns, interaction of 3 dishes. But if you just take the measurement as it's crossing the center, then you should be okay. All right. And so that's what I'm looking at is, you can look at all the other stuff. They may or may not interact like that. So if I use that same formula, the total gain formula, but I use it on a north and south antenna, but now I vary the elevation angle between 0 and 90 degrees for elevation. Okay. This is what it looks like with you got elevation on the bottom. And the assumption is that your object is dead center between the two antenna 1 and 2. And then this one is behind it. You get this. This is what it looks like if you change elevation, that angle to, what you used to think was offset angle for the drift scan, but now I'm using it as elevation. I'm going like this. So now the gain properties look like that. Well, what's the problem with that? Depending on where I'm looking, I'm going to fix that antenna in the sky at a certain elevation angle. If I fix it wrong, I could be in one of the troughs. That's the problem with this whole thing. So now why doesn't that work with Radio Jove? Because Radio Jove puts a phase thing in there and is basically looking broadband at that general piece of the sky. So it's moving the beam down. Here, this is 2 antennas that they're pointed in the right direction from the start, but now you see fringes because the standard fringe pattern happens. Okay, so if I actually sat there and I did this automatically with the antenna, that would show up on a north-south interferometer. So that's the problem is, how can you guys use that without ending up in a trough and then basically canceling out one of your dishes? So what I did is I took that formula again. I said, hey, if you think of 1420 megahertz, that's 21 centimeters, right? 0.21 meters. So an entire phase of that in order to shift that waveform over between fully in line to totally 180 degrees out of line is only 21 centimeters. Every 21 centimeters, I restart the phasing. So that's not a lot. So either I move the antenna in baseline, or I put like what Radio Job does, they actually put a phase cable in there to actually have more distance for it to move. But they don't change that on a regular basis. They change it like just to get, because they got a big wide beam width. Here you've got a very narrow beam width, and you got to actually plan on getting this. You got to aim properly in elevation, but if you can't aim properly in elevation, the other variable is change the baseline north-south to make this work. So what I did here is, this is an example of the first one. The blue line was that original one I showed you, and that was 2 meters baseline between the two antennas, north-south antennas. I simply moved it 0.2 meters, and I was able to shift the entire phase, the gain phase, to the right. What does that mean? That means that if I know where I'm going to look, if I'm looking at an object that's at 30 degrees elevation, and I'm planning on that, I can move the baseline in order to maximize my gain at that elevation from the north-south point. See the way it works? So that's the whole base of this thing, is you got to take care of both, and it doesn't work the same with east-west, because east-west is you're at a set elevation and you're counting on the drift scan to cause your fringes to happen. Here, the fringes, you're only getting 1 point because you're stuck there and the target's moving across one elevation. All right, so you won't see this fringe pattern, but you will see is your gain will be up or down depending on where you aimed and depending on what the fringe pattern is north-south. Okay, so if I use that 2 meters again, my original thing, this is what the fringe pattern looks like for all 3 antennas. And you can see if I just add them up without interferometry, that's the blue line. So that's my goal. That's my maximum goal possible because of pointing loss that I could possibly get on gain. All right. You see how low adding the 3rd antenna actually drops the signal because I chose the wrong. I ended up in a trough. And this is by trial and error, but I think I could do it a different way. If I move the baseline, here I moved it at 0.24 meters. I move that line there to maximize it. So now I'm up in the top instead of having in a trough. And that's simply, and you can calculate, it was very simple to calculate. Here I just simply started adding 0.1, 0.2, but you can actually automate that really easy. And so that's what it now looks like. So you see how I've now maximized the gain, maximized everything with that 3rd dish. And that gives you the progression of beam width. So here is I've got the beam width of basically a single dish with no interferometry, an east-west interferometer beam width, and now I've got a third north-south one, and I've totally dropped the north-south, east-west beam widths of the thing using interferometry. Only if I chose my north-south baseline correctly. East-west baseline, it doesn't care because the center offset is going to be the highest no matter what. And you just get your fringe spacing will be either high or low. The north-south matters because of that trough effect, depending on your elevation. So if you so you need to do this thing first, figure out what you want to look at, figure out its elevation, and then adjust your baseline to make sure you maximize your gain at that elevation. Okay. And also the ramifications of this is Now, what if I do something with the antennas, like I change, one is, if I move the antenna, somehow the feeds are changing distances, or, all that is affected. So this basically gets you zoomed into the fact that those feeds have to be exactly that far apart. And in moving them up and down and stuff like that may change that baseline distance somehow. All right, so big picture, the thought, so my thought experiment is, can we go put together a small interferometer? Can we use this to help calculate the output parameters of that, so we can test that against theory using all the basic formulas, which are all basic. You see, I didn't put any real hard formulas up there. And easy to model. I actually modeled it in Excel first. That's how easy it is. And then I shifted over to MATLAB because it gave me pretty pictures. So the east-west interferometer, obviously the beam width, the narrow is better. Third antenna will decrease the beam width north-south. So now we got a smaller one. The problem I don't understand yet is when you actually phase all those things together as they're going through drift scan, and you got that third antenna, are there other third party mixing that I don't know about? I sort of eliminate that by saying you're only taking a measurement when the target is actually dead center between the two east-west ones, and the third antenna is right in the middle of them. So at that single point, you're going to get maximum gain from the east-west, and the maximum gain, if you chose it right, north-south. And you don't have all that. It may not look like a clean fringes. I'm just saying, as it goes through drift scan, it appears that on this, but there might be third-party mixing that makes jumble all that stuff up. So this model suggests that you guys can take a couple small dishes, add a third dish, and come up with a very north, south, east, west. Everybody's seen the east, west ones. There's a bunch of people who are doing east, west. In fact, one of the reasons I was doing this is because Wolfgang showed his east, west interferometer and showed out how good the resolution he was getting. But what he doesn't show is that the north, south was really not that good a resolution. So you get the smearing north, south, because these interferometers don't help you north, south. They just help you east, west. All right. And so, and talking to Ted Klein, who's actually trying to build Yagi interferometers, we're going to try to put a third north-south one on. The softwares don't count for it either. It assumes that the north-south is the same as the east-west beam width in all the software packages, but they're not. They're smeared north-south. And I view this as a pixel. What you're looking at is pixels, is beam width. Assume this is a pixel, right, in your camera. And the target is this little point in the middle, and the average of that target and this extra noise out here, they take the average of that, and that turns into the intensity of your pixel. Okay, so when you're looking at all this extra stuff and not your target, that pixel is minimized, or it's actually less bright than it could be. As you get smaller, the ratio of that that target is bigger than it was from the average of the total area of that thing. So it looks brighter. So if you do it, and you do all the way down the bottom, you've just reduced all your noise, and your target's still the same intensity. So you should get that a lot brighter, and basically your gain, right? So so that's the whole theory on this thing, is that use your phone connection. You know, how many pixels do I got in my phone? You're basically reducing your pixel size resolution on your radio telescope using on north, south, and east, west to make it look smaller. So your intensity is better resolution, better gain on everything. Okay. And here's a bunch of the book I like here is Fundamentals of Radio Astronomy Observational Methods. He basically goes into Krauss's book on radio astronomy, but he makes it, how do I use some of these formulas to do better? And that's how he basically outlined that one formula. And then I converted that formula to total gain. I'll have this model sitting up in Drake's Lounge. Anyone wants to play with it? Put in, if you got an interferometer in mind, you can sit there and put all the numbers in and run it and come up with these, whatever the picture looks like.